What is the theme of today's class? So today we are going to talk about binary search, but the harder parts of it, some harder parts of binary search. So just to get started, I'll tell you there is one very important concept. It's a beautiful concept. And I can tell you that 99% of questions which are asked in interview on binary search and questions which are especially hard or tricky, the good ones, they belong to this concept. So it is a remarkably important concept and we will first grasp it. It's very easy to grasp. It's not hard. It's very easy to grasp. The questions could be tricky. Where it is applied, the application of it could be little tricky. Okay, but let's first get the concept. So all of us know, all of us have some idea about binary search, right? We all know that if we have an ordered space, for example, let's say you have an ordered array, something like this. And now let's say you have to search for an element. Let's say you have to search for 13. Then what do you do in binary search? You pick the middle point and you check what is the value. So here the value is 7. 7 is smaller than 13 and your array is sorted. So you can say that your answer lies in the right half. Okay. On the other hand, if let's say your target was not 13, it was 2. In that case, you would have said that 7 is greater than 2. So my answer lies in the left half. So you either switch to the right half or you switch to the left half. Why you are able to make this switch is because of the fact that your input is ordered. Okay. Now, let me tell you that in a lot of questions of binary search, you might not have a sorted array. In fact, you might not even have an array. Okay. So we will experience some questions like those. But before that, let me ask you, do you know about monotonic function? Do you understand what is the meaning of monotonic function? It says monotone. I mean, there is exactly one tone inside it. So if we have a function, let's say I'm drawing x and y axis. Now there is a function which just increases, or there is a function which just decreases. Then such functions are called as monotonic because they do not have two tones in them. It's not like they increase also and then later they decrease also. So contrary to it, if let's say you have a function like this, is this monotonic? Would you call this function as monotonic? The answer is no. This is not monotonic, but both of them are monotonic. Okay. So the trait of a monotonic function is that your monotonic function, whatever it is, it would either be increasing by nature or it would be decreasing by nature. Yes, at certain points, it can be stable also. So for example, let's say I plot x and y axis. And let's say you have a function which is whose graph is, let's say, looking like this. Is this function monotonic? Yes, it is monotonic. Why? Because it is just increasing. I mean, let's say this particular point, call it A, this particular point, call it B. So as you move from A to B, the values are only increasing. Yeah, at certain points they are stable, but that's all right. It never happens that the values are decreasing. They are just kind of increasing. So this is a monotonically increasing function. Similarly, what kind of function do you think this is? This is a monotonically decreasing function because here, as you move rightwards, you will see that the values are decreasing. Certain times they are, same, but that's all right. So this is monotonically increasing function. This is monotonically decreasing function. All right. Now, what is an important trait of such monotonically increasing function? So if you look at any function that monotonically increases, let's say for instance this, Here, if I consider 2 points, let's say my first point is this, let's call it x1, and second point is this, let's say x2, okay? And x1 is behind x2. So what I mean by that is x1 is smaller than or equal to x2, okay? Or remove this equal to sign also. Let's say x1 is smaller than x2. So if this is the case that x1 is smaller than x2, can you tell me the relationship between f of x1 and f of x2? What is f of x1? F of x1 is this value, the height at this point. And what is f of x2? F of x2 is this value, the height at this point. So what will be this relationship? For guarantee, I can say that this height will be smaller than or equal to this height. Because we all know that if this function is monotonically increasing, as you move front, the values will never decrease. What are the values? The values are these heights. So these heights will either be same or the other height will be greater. So does everyone understand this thing? How many of you are clear with this? So this is an important trait which is true for what kind of functions? Monotonically increasing functions, right? Okay, now what if this was a monotonically decreasing function? Let's say I plot something like this. In this case, let's say, again, you have a point A, another point B, and A is behind B. That is, A is smaller than B. So what will be the relationship between f of A and f of B? You can see this is f of A, this height, and this is f of B. So it is guaranteed that f of A will be greater than or equal to f of B, right? Because as you move front, the heights decrease, okay? So the height at this point will be smaller than or equal to the height at that point. So this is one key difference between monotonically increasing and decreasing. Now, why are we talking about it? At what point it is going to be useful for us? For that, let us take a question. We'll take a very simple question. I think all of us can solve a problem if we are given a sorted array and somebody asks us that, hey, there is a key. Just search this key. Can you use binary search to search this key, whether it's present in our array or not? All of us can do it. All of us can do it in log of n time by using simple idea of binary search. Now, there is a different variation of this question where you are told that, hey, this time you have been given a function. Now, this function is defined from, let's say, point A all the way till point B. It is defined from point A to point B, and this function is monotonically increasing by nature. Okay, for example, let's say it kind of looks like this. Okay, now you have been given a value key, or let's call it k this time. Let's say you have been given a value k. Let's say k is equals to 15. Okay, so maybe I'll point 15 somewhere. Let's say this value on the y-axis is 15. So we have to find point on the number line. We have to find a point for which f of x is equal to 15. So what is that value of x for which f of x is 15? This is what we want to determine. Okay, like for example, let us say that this value 15, it was being achieved at this point. And let's say this point was 12, right? Then your answer should be 12. So what you have been given is value of the function. And what you have to find is that at what point on the x-axis that value is actually being achieved. This is what we want to solve. Is it making sense? How many of you understand what we are trying to solve. Can we solve it? Okay, so let's see what idea we can use. We all know that this function from point A to point B, from here till here, it has a monotonically increasing trend. We can see that the values are all just increasing, right? Now, can we exploit this fact and get the job done somehow? Yeah, some of you have thought about the right thing, which is binary search. So how many of you think that the idea of binary search can be elegantly applied over here? How many of you feel like that? Yeah, very good. Let's see how it can be applied. We can say that, hey, let's say our lower bound, you have low and high in binary search, right? So let's say your low is A and your high is B. Now you can find a midpoint. Your mid is always computed as low plus high by 2, which is the exact midpoint. Let's say your midpoint happens to be this. And the value at this point was, let's say, 11. Let's call it mid. If f of mid is smaller than 15, what would it mean? Would your answer lie in the left realm, or would it lie in the right realm? Would it lie in the left side or right side? It would definitely lie in the right side. Why? Because I know that if at this point the value is 11, then behind this, the values will be even smaller than 11. And I am looking for a point where the value should be 15, which is greater than 11. So I should hook myself to the right side. All right. Similarly, now imagine, just imagine that um, the value of mid, which you had. So let's say the value of mid, which you had, was somewhere here. Okay. And you found out that f of mid is, let's say, equals to 19. So if f of mid is equals to 19, if f of mid is greater than 15, in that case, you would say that, hey, my answer lies to the left side and not the right side. So do you see that it's the exact same idea of binary search which is being used? And what is the key idea? That depending on the relationship between f of mid and key, the relationship between f of mid and key, the key was 15, right? You choose either the right side or the left side. And based on that, you get your job done. This is the concept which I wanted to talk about. Now, this same idea can be used if our graph is in monotonically decreasing form also. The exact same idea can be used with just little bit variation. I mean, the conditions where you are going right here, in those conditions, you will come left here. And the conditions where you are going left here, you will go right here. Is this concept making sense? How many of you could relate to it? What we just did over here. Yeah. Okay. Even if you could relate to maybe 50%, 60%, whatever percent, that's good enough. That's really good enough because based on this, we can lay our further foundations. Okay. See, guys, I'll tell you one thing. You must have seen a lot of problems where it is said that, hey, you have an array which consists of zeros and ones. So initially you have zeros and then you have some ones. And what you have to find is you have to find the index of first one. Find me the index of first one. What will be output in this case? 0, 1, 2, 3, 4, 5. The index of first one is 5. So my output should be 5. You can solve this question using binary search. All of us can solve this question using binary search, right? We can say that if our mid is 0, we will go to the right side. And if our mid is 1, then in that case, what will we do? I mean, there are two possibilities. Either we could be pointing to the answer or we would be to the right side of the answer. So if we are to the right side of answer, we will come left. And if we are pointing to the answer, if behind this there is a 0, this itself is our answer. So this is the idea. Yeah, you can also use lower bound. Lower bound does exactly same thing, okay, which binary search does. So both of the approaches are completely all right. Now, what I'm trying to tell you from here is that, guys, this scenario can be plotted as a graph. And why I'm doing that is to just give you a feel of what we are about to do. I can say that, let's just quickly plot a graph, and these indices 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever they are, let's number them 0, 1, 2, 3, 4, 5, 6, 7, 8. And now I can say from 0, 1, 2, 3, 4. From 0 to 4, the values are 0. So here the value is 0. 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 At 5, the value is 1. At 6, the value is 1. At 7, the value is 1. At 8, the value is 1. Now, if I connect these, this thing is also a monotonic function. Is it not a monotonic array? Yes, it is a monotonic array. Now, what you see here is also a monotonic function. Now, if somebody asks me that, hey, in this monotonic function, tell me the first value of x such that f of x is 1. Can you find that out using binary search? Yes, exactly you can. So whatever you were doing here, the same idea can be applied here also. So, you are about to see a lot of problems on binary search where you will have graphs of this kind. And the question will be either find me this point or find me this point, which is either find me the first point where value is true or find me the last point where value is false. Imagine there is a Boolean function whose values can either be false or true. Just imagine that. Okay. So now further it is monotonic. Let's say it is monotonic. So at 0 it is false, at 1 it is false, at 2 it is false, and later on it is true, 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 till infinity it is true. So somebody might ask you that, hey, tell me the last point where it was false, or tell me the first point where it was true. So such kind of questions we are going to see. So let's get started with a very, very super important question. If you understand that, you understand everything. Okay. So you'll have to focus a lot for the next 20-25 minutes or so. Okay. So, and you will have to watch everything till the end. It's not like if you see half of it, you will get half of it. No. If you see 100%, you will get 100%. If you see 99%, you may get 0%. That is the thing with it. Okay. So the question is like this. You have an array, and let's say this array contains 40, 10, 10, 30, 40, 20, 50, 70, and 50. Let's say just this much. And you have been given another integer k equals to 6. You have to find the kth smallest element. Kth smallest element in the array. What is kth smallest element in array? Kth smallest element is that element which occurs at kth place, which is index k minus 1. Why index k minus 1? Because indexing is from 0, right? Which occurs at index k minus 1 after sorting. I mean, it's common sense, right? If you have an input and somebody is asking you, hey, tell me the sixth smallest element. What is the easiest way to find sixth smallest element? You will just sort the array, and the element which will be present at index 5, which is the sixth position, that would be your answer. So yeah, you can use a heap. We'll talk about the different solutions that you can come up with here. But can you quickly tell me what will be the output in this case? So let us say somebody sorts this array. Upon sorting, what will you get? You will get 10, 10, 20, and then you have 30. And after 30, what do you have? You have 2 times 40, okay? And after 2 times 40, you have 2 times 50, and there is 170. Did I miss anything? 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 3, 6, 9. Yeah, all are done. So element at fifth position, 0, 1, 2, 3, 4, 5 is 40. So your answer should be 40. Yeah. Now there are varieties of ways to solve this question. A lot of you are talking about heap. So see guys, the moment you use heap, there is extra space involved in it. Okay, just mind it. I'm not saying that this is a bad approach or something, but be mindful of it, okay? That there is extra space involved in it. Uh, Tell me what is the easiest solution which comes to your head? The easiest solution which comes to your head, I believe, could be that, hey, just sort the array and return array of k minus 1. As simple as that, right? Very good. What is the time complexity of this approach? The time complexity is n log n, which is the time complexity of sorting. And what is the space complexity? Did we use any extra space? No. So the space complexity is order n. Okay. Now, the question is telling that you cannot modify the array, cannot modify the input. It's a read-only array. If it is a read-only array, you cannot modify it. What will you do in that case? So yeah, very clever. A lot of you would definitely have come up with it that, hey, we cannot sort the input, right? But we can definitely create a temporary array, which is nothing but a copy of the initial array. So just copy all the elements of input in this temporary array, sort this array and return the element at k minus 1. Yeah. So in that case, you are not modifying the input array and you are still solving the problem in n log n time. But what is your space complexity? If you resort to this kind of tactic, what is your space complexity? Yeah, your space complexity in that case will become order of n. So now the question further says that, hey, I want order one space. So I want order one space and I want no modification of input. Now it becomes a really good question. Okay, so how can you now go about it? See, these are the points where your brain goes out of the comfort zone, okay? And then you see a scope of growth because maybe something new is coming. How many of you feel stuck at this point of time? After I am enforcing these two constraints, how many of you feel like, ab kya kare? What to do next, right? So this is where something useful is going to come and we will talk about it. So let us understand that. But you will have to hear me very carefully. See, uh, let's say you have a random array, okay? Let's just take any random array, 5, 6, 1, 5, 4, 3, 2. And let's say the value of k is 4, okay? What is the fourth smallest element? So if somebody writes this array in sorted form, it would be 1, followed by 2, followed by 3, 4, 5, 5, and 6. 4 means third position, right? 0, 1, 2, 3. So it is 4. Luckily, it is 4 only, right? Okay. Now, tell me what is the characteristic of kth smallest element? I'm asking for what is the characteristic of kth smallest element? So whatever is your kth smallest element, if let's say I come up with something which is count of elements which are smaller or equal, count of elements smaller or equal than a particular value, let's say 4. So I have created a function count which takes a number num and tells me that in a given array how many elements are smaller than or equal to this number num. Let us say your number num is 3 and your array is like 7, 1, 1, 3, 4, 2. Can you tell me what will this function return? Given that this is the job of the function. The job of function is to return that how many elements of the array are smaller or equal to this number. So how many elements of this array are smaller or equal to 3? You can see this, and that. So the value is 4. Now I am talking in terms of this count. Okay, so please remember, whenever I say count from now on, you just understand I am talking about this count function. Okay, yeah. Now come back to this thing where I was talking about the characteristic of kth smallest function. Um, if something is truly your kth smallest element, let's say 4 is truly your kth smallest element, then what will be the count of 4? Or what will be the count of x? Let's say if this element was x, which was my fourth smallest element, what will be count of x? Can I say this value will be greater than or equal to k? Because imagine, just understand, if something is kth smallest element, then that would be at index k minus 1. Let's say x is your kth smallest element. Then that would be at this index, right? Now, all the elements before this would be smaller than or equal to x, right? Now, if you are counting that how many elements are smaller than equals to x, it is guaranteed that at least k of them will be there. Because from 0 till k minus 1, how many elements are there? There are k elements. So it is guaranteed that the value of count of x will at least be equal to k. At least it will be equal to k. And if there are duplicates of this x, which is quite likely, if let's say this x is repeated further, then the count can even be greater than k. So I can say that, hey, if something is actually my kth smallest element, then count of that will be greater than or equal to k. Why? Because if that is kth smallest element, that will be standing at kth position. So there are at least k elements which are smaller than or equal to it. And if there are duplications, then this count will be greater. Do you understand this thing? The logic behind this thing? How many of you get it? This is the crux. This is the starting point. If you got it, we can move ahead. Okay, once more. So I'll do it once more. Just listen very carefully. Did you understand the definition of this function? Did everyone get what this function stands for? This count of num, it simply tells us that in this array, how many elements are smaller than or equal to num. That's all. So let's say if your num is 3, it will count how many elements are smaller than equal to 3. राइट तो इस अरे में कितने एलिमेंट्स दिख रहे हैं जो 3 के बराबर या 3 से छोटे हैं हाउ मेनी सच एलिमेंट्स आर देयर दिस एंड दैट 4 ऑफ देम ओके तो अब जब भी मैं काउंट बोलूंगा काउंट ऑफ एक्स बोलूंगा तो समझ जाना व्हाट आई मीन व्हेनेवर आई से काउंट ऑफ एक्स माय इंटेंशन इज टू नो that how many elements in this array are smaller than or equal to x. Now, what I am telling you is, if let's say your kth smallest element is something, let's say your kth smallest element is 9. So in sorted array, it would be at index k minus 1. And behind it, all the elements would be smaller than or equal to 9, right? So if somebody asks you, hey, what is the value of count of 9? You will say that there are already k elements. From 0 to k, there are already k elements which are smaller than equal to 9. So at worst, this value will be equal to k. But if this 9 is further repeated, which is possible, then this count can even be greater than that. So it is guaranteed that count of 9 will be greater than equal to k. And this is what I am generalizing. How I am generalizing is that if something, and I am calling that something as x, if let's say x is your answer, if x is your kth smallest element, then that would be appearing at index k minus 1. So count of x is guaranteed to be greater than equal to k. Those of you who did not get it in the first go, do you now understand it? Let's not, fixate ourselves about the time complexity. It is not order n square. It is way better than that. Okay, I'll show that to you in some time. It's just the beginning pieces right now, okay? That you understand there is a count function and how it is defined. Now, my question to you is, what do you think about the nature of this count? Is this monotonic? Let's say you have an array which contains 2, 1, 4, 5, 3, 3, 6. Let's say I'm passing the value of x as 2. Can you tell me what will be the output? How many elements of this array are smaller than or equal to 2? Two of them, right? Now, if I increase my input, let's say if the value of x is 4, what will now be output? 1, 2, 3, 4, 5. There are 5 elements which are smaller than equal to 4. Do you see that if my input is increasing, then output is also increasing? And that is exactly what is the trait of monotonic function. That if you go from point 2 to point 4, then the height increases. If your input increases, then the output also increases. And it's common sense that it will be a monotonic function. Why it's common sense? Think of it in this manner. You have an array. Let's sort it. 1, 2, 3, 3, 4, 5, 6. Somebody has asked you that tell me how many elements are smaller than equal to 3. You will say this much. Now somebody has asked you, tell me how many elements are smaller than equals to 5. You will say this. Can you see that this thing already encompasses this, right? So if the value of x increases, then the number will be farther. And if the number is farther, the count will be more. Do you get this idea? So what that means is that this function is clearly monotonic. Now that is one great point. Okay. Now what we ended up realizing was that, hey, if something is our kth smallest element, let's call that something as x, then count of x is guaranteed to be greater than equal to k, right? Now, let me ask you the reverse question of it. Let's say you got a value of x for which count of x was smaller than k. Okay. Let's say, let's go back to, let's look at this case itself. Okay. Let's say k is equals to 5. So 0, 1, 2, 3, 4. So your fifth smallest element over here is 4. So if you take count of an element, let's say y, and you got this count as smaller than 5, then what does it mean? It means that y must be smaller than 4. It means y must be smaller than 4, isn't it? See, if you find out the count of 3 is 4, which is smaller than 5. Count of 2 is 2, which is smaller than 5. Count of 1 is 1, which is smaller than 5. So if you have a number for which count is smaller than k, it means that that number is smaller than your answer. So your answer actually lies towards the right side. Do you get this point? Right? But on the other hand, okay, so let's do one thing. What we are going to do is we'll consider this array and we will plot a graph. So on this graph, here you have count values and here you have the numbers x. Okay. Uh, okay, tell me, for x equals to 1, what is the count? How many elements are smaller than equal to 1? Only 1. Okay. So here the value is 1. Okay. Let's consider x equals to 2. What is the functional value at x equals to 2? How many elements are smaller than equals to 2? 2 of them. So here the value will be 2. X equals to 3. How many elements are smaller than equals to 3? 4 of them. 4 of them. So here at 3, the value would be 4. X equals to 4. All right. At x equals to 4, what will be the value? What will be the count? How many elements are smaller than equals to 4? There are 5 of those. Let's say this point was 5. Similarly, at x equals to 5, how many elements are smaller than equals to 5? 6 of them. And how many elements are smaller than equals to 6? 7 of them. Now, those of you who did not realize it before, now do you realize that it is a monotonic function? Yes or no? First of all, you realize it is monotonic. This is monotonic, right? Okay. Now, what I am saying is, what is your actual answer for k equals to 5? What is your actual answer in this array? Hmm? 4, right? 4. At 4, what is the value of count? At 4, yeah, sorry, at 4, the value of count is 5, which is k. Remember, this 5 is your k. It's given here, right? Now, what I am saying is that if for some value, the count was smaller than k, like you can see, for 3, the value is 4. For 2, the value is 1. For 1, the value is 1. So if for some values, the count comes out to be smaller than k, what does that mean? That means that value is smaller than your actual answer. So your answer must be lying in the right side. Do you now get this point? How many of you get this point now? Right? Okay, great. Now, if at this point 4, you got a value which was k, then at point 5, at point 6, at point 7, at point 8, at all these points, you will get the values which are even greater than k. I mean, greater than equal to k. What is it that we want to find? So if you look at this thing carefully, I would say that, hey, look, these are the points where count is smaller than k, and these are the points where count is greater than equal to k. What will be my answer? My answer will be the first such point where count is greater than equal to k. And if you try to relate to it, it is exactly what I had said to you a few slides ago, where I told you that, hey, like I gave you an example, right? That there may be some zeros and some ones, right? Some points like this, and some points like true, true, true. And you might have to either find this or that. The same thing you have to do here, because the first such point where value is greater than equal to k, that happens to be your answer. That happens to be your kth smallest element, right? So that's what we have got to do. Do you understand what point we have to find? So this is your function. This entire thing is your function. In this function, we have to somehow find this point that, hey, what is that first point where the value is greater than or equal to k? Just find that point out for me. So how we can find that point out? Can we apply binary search in this range? Why 3 won't be the answer? For value 3, we are getting count 4. And what is the value of k? Is it 4? No, it is 5. So if something is your fifth smallest element, the number of elements which are smaller than equals to that is 5, is not 4. Okay. So 3, for 3, the count is 4. That means 3 is smaller than your answer. You get the point? So let's say you are trying your luck for 3 and you found that, hey, for 3, the number of elements that are smaller than equal to 3 is 4. So you can immediately discard 3 and everything behind 3. And you will say that your answer is lying in the right side. Okay. So carefully looking at it, I can say that imagine this function is defined in a range. So this function is monotonic from low to high. It is monotonic from low to high. Okay. Okay, we'll again talk about the complexities at a later stage, and we will see whatever we have done is more efficient or less efficient. Okay, but to do that, we first need to reason about whatever we are doing is right or wrong. So let's focus on that. Of course, it is much, much optimal. Don't worry about that. So, yeah, this function, I can say, let's say it is defined from 1 to 8. 1 to 8. Now, I can find a midpoint, and at that midpoint, I can find the value of count of mid. If this count of mid comes out to be smaller than k, let's say your mid was 3, or it was 2, or it was 1, and this height was smaller than k, what will you do in this case? You will say that, hey, your answer is definitely greater than mid. And because your answer is greater than mid, now you would want that your search space should be from mid plus 1 to high. So yeah, you'll go right and you will do low equals to mid plus 1. Do you understand what we are doing here and why we are doing this? Yeah. Okay. On the other hand, if count of mid is greater than equal to k, mind it. If count of mid is greater than equal to k, that means you are in this zone, correct? Correct? Because for all of these values, 4, 5, 6, 7, 8, the count that you have got is greater than equal to 5. Now, how do you decide? How do you decide whether you are at answer or not? So for that, what you can do is you can immediately check. You can immediately check the count for m minus 1. Okay, the array is not sorted, and we'll see if it is sorted, whether sorted, unsorted, doesn't make a difference. So I'm saying here we will check the count of mid minus 1. Why I'm checking count of mid minus 1? Because let's say we were at 4. At this point of time, the count was greater than equal to k. Count of 3 must have been smaller than k. If it happens, then I can say this is my answer. But if let's say your mid was here, if your mid was here, although the count is greater than equal to k, but this is not your answer. And how you can ascertain that? You can ascertain that by checking count of 6. You will see that, hey, count of 6 is also greater than equal to k. So in that case, you will say my answer lies to the left side, right? So in why we are checking for count of mid minus 1 is to just ensure whether this mid is our answer or not. Yeah. Yeah, there is a possibility that mid might not exist in the array. There is a good possibility for that. And I'll show you that in the dry run. But it is guaranteed that the smallest value of mid for which count will be greater than equal to k will definitely be present in the array. It will definitely be present in the array. Just imagine, let's say you had 10, 20, 30, 30, 40. Okay. So if let's say you have a value 41, if let's say your mid is 41, you will get a count of 5, right? But in that case, you would want to check for mid minus 1, 40. I told you, whenever your count of mid is greater than equal to k, you check what is the value for mid minus 1. If for mid minus 1 also it is greater than equal to k, then you say that mid is not your answer. Your answer is lying in the left side. Okay. And if you take a look, 40 is the smallest possible value for which, in fact, 40 is that particular value for which you will see that count of 40 is greater than equal to 5, but count of 39 is smaller than 5. And that being the reason, you will avoid 40 as your answer because this is the point which we wanted, right? This is the point which we wanted, at which the count is greater than equal to k, the transitioning point, right? At which the value is greater than equal to k, but behind it, the value is smaller. So this is the logic which we will have to kind of keep. I'll show you a dry run of it, and then it'll make lots and lots of sense. But before that, is the logic clear? How many of you kind of got the logic? How did this emerge? Okay, let's look at a dry run and it will reinforce everything that we have talked. Okay, what was our initial array? It was 40, 10, 10, 30, 40, and then 20, 50, 70, and what else? 50. And the value of k was 6. Okay. Uh, Tell me one thing. Can you define a range, low and high? What can be the smallest value of my answer? The smallest value of my answer can be 10, which is the minimum element in the array. And the largest value of my answer can be how much? Think about it. 70, which is the largest element in the array. I mean, it's common sense, right? Your kth smallest element in the array can never be smaller than your minimum and can never be larger than your maximum. It's guaranteed for sure, right? Okay. So now, okay, if I take this array as an example, your mid will be 40 and there itself you will get an answer. So what I'm going to do is I'm just going to make slight change to it. That slight change would just be that instead of taking this 70, I would say, let's take 90. So our high is, let's say 90. Now, so our range is from 10 to 90. We will pick a midpoint. What will be the mid? 50, right? Okay. Can you tell me what is the value of count of 50? How many elements are smaller than equal to 50? 1, 2, 3, 4, 5, 6, 7, 8. 8 elements. And this value 8 is greater than equal to k. Mind it. So what does it mean? Does it mean that our 50 is greater than the actual answer or smaller than the actual answer? It is greater than the actual answer, right? That is what you had seen there in the graph. That value is towards the right side. That is the reason the height that you are getting is greater than equal to k. So in order to ascertain whether this actually is my answer or not, what should I do? I should immediately check count of 49. And what will be count of 49? How many elements are smaller than equals to 49? 1, 2, 3, 4, 5, 6. Now this value is also greater than equal to k. So what does it mean? It means that our answer is smaller than 50. Correct? If our answer is smaller than 50, we will go to the left half. Going to the left half means we will change our high to mid minus 1. When you change your high to mid minus 1, can you quickly tell me what will be your new range? Low तो वैसा का वैसा ही रहेगा. Low will be 10. And what will be your high? Your high will be mid minus 1, which is 49. Very good. Now you will compute your mid again. What will be your mid? 59 by 2. And how much is 59 by 2? Can somebody help me with that? 29, right? Okay. What will be count of 29? Let's everyone count how many elements are smaller than equals to 29. 1, 2, 3, right? Okay, 3. When the count is smaller than k, इस केस में हम क्या करते हैं? What do we do in this case? We say that, hey, it is guaranteed that this is smaller than our answer. And if it is smaller than our answer, we will go to the right side. Going to the right side means we will change low equals to mid plus 1. If you change low equals to mid plus 1, what will be the value of low? 30. And now your range will become 30 to 49. Again, you will find your mid. What is your mid now? It is 79 by 2, which is 39, right? And what is count of 39? Just check how many elements are smaller than equals to 39. 1, 2, 3, and 4. Yeah, 4. 4. 4 of them. This value 4 is smaller than k. Remember, your k was 6. So what does it mean? It means that our answer is greater than 39. So we will again change our low to mid plus 1. So what will be our low now? 40. So now our range is from 40. Do you observe how our range is shrinking? This range is half the size of that. This range is half the size of that. This range is half the size of that. Okay, let's continue. What will be mid now? Yeah, a lot of you answered 44. Very good. What is count of 44? How many elements are smaller than equals to 44? 1, 2, 3, 4, 5, 6. Yeah, 6. So there are 6 elements which are smaller than equals to 44. Now, what is this value 6? It is greater than equal to k. If it is greater than equal to k, this might be our answer. But how to check if this is our answer? Quickly check count of 43. Okay, what is count of 43? You will see that count of 43, 1, 2, 3, 4, 5, 6. Count of 43 is also 6. Count of 43 is also 6. So what does it mean? It means that hey, 44 is not our answer. Our answer is something smaller than it. So you go to the left side. So you do high equals to mid minus 1. The moment you do that, now your range becomes 40 to 43. And you find midpoint again. What is your midpoint? 41. What is count of 41? Just find out how many elements are smaller than equals to 41. It will again come out to be 6. In fact, it is 6. I have counted it. Don't worry. Whenever it happens, we check for mid minus 1. What is count of 40? Count of 40 is also 6, which is greater than equal to k. What does it mean? It means that our answer is definitely smaller than 41. So we will again do high equals to mid minus 1. And now our range will be 40 to 40. Find the mid. What is mid? 40. What is count of 40? You already found it before. 6. Whenever it happens, you find out the count of mid minus 1. And what is the count of mid minus 1? How many elements are smaller than equals to 39? 1, 2, 3, 4, just 4. Whenever it happens, that count of mid is greater than equal to k, but count of mid minus 1 is smaller than k, that mid itself is our answer. So we can immediately return 40 over here, and that is what our answer is. You relate? Count of mid is greater than equal to k, but count of mid minus 1 is smaller than k. That is the transition point, and that is the answer. Just look here. Count of 4 was greater than equal to 5, and count of 3 was smaller than 5. That's the idea. So how many of you understood it? How many of you could completely relate to the dry run? Yeah. So that is how it works. Now, if you carefully look at it, what will be the time complexity? Because a lot of you had concerns regarding time complexity. So can you talk about it? Let's see. What is our initial range? Our initial range is from min to max. This min is the minimum element of array, and this max is the maximum element of array. Correct? And in every step, the range is becoming half, half, half. So the initial size of your range is max minus min. And every time it is becoming half, 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 half. So number of iterations will be log of this thing base 2. Now, in every step, what we are doing is we are invoking count function. And what will be the complexity of count function? Just order n. Because in order n time, just by doing one traversal, I can count how many elements are smaller than equal to something. So the complexity is n multiplied by log of max minus min, which is much, much better than n square or anything else. Now, the key thing to note here is, see, this is almost same as n log n. You understand? Because log is a very slowly growing function. So there is not much difference between this and this. And in certain cases, this might be better. Let's say you have a huge array. You have an array of size 10 power 6. But the elements that you have are very close to each other. So let's say the smallest element you had was 10 and the largest element you had was 100. So this thing will be very small in that case. And now that will be Max minus min very, very greater than n, there are also no issues as I told you, because log of anything is very slowly growing function. What can be the maximum value of this expression? Let's say max is 10 power 18 and this is 0. What is log of 10 power 18 base 2? It is 18 multiplied by log of 10 base 2. Log of 10 base 2 is approximately 3 or 4. So this thing, this poor thing is something in between 60 to 70. So your complexity is 60 to 70 into n, which is nothing. It's nothing, right? In this particular case, did we use any extra space? Did we use any extra space? No. Did we modify our existing array? No. So we have ticked all the checkboxes and still we have been able to solve this question. Now, if you have to code it, I'll show you the template behind it. It's very, very simple. Find the minimum element. You can do that and you can say your low is equal to that minimum. Find the maximum element and you can say your high is equals to that maximum. And now the typical code of binary search, how does it look like? While low is smaller than equal to high, what do? You find out your midpoint. Your mid is low plus high by 2. And then you invoke count of m from where you get a value, let's say c. If the count you got is smaller than k, what do you do in this case? Let me help you recall. If the count comes out to be smaller, you go to the right side. You change your low. Yeah. So in this case, you do low equals to mid plus 1. And what do you do in the else case? In the else case, let me help you recall again. You quickly check for mid minus 1. You quickly check what is the value that you are getting for mid minus 1. So you can invoke count for mid minus 1 and let's say this value is C1. Now, if C1 is smaller than K, it is guaranteed that your current mid is the answer. So you can return mid. But in the else case, you will say that your answer lies in the left side. So you will change your high and you will change it to mid minus 1. Is that clear? How many of you understand this? Yeah, to avoid integer overflow, you can use that. It depends upon, I mean, another way to avoid integer overflow, I mean, for practical purposes, if you are sitting in a coding contest or something like that, you can use a long data type or something. And also you can look at the possible values of your low and high. And it's not necessary that every time you will get integer overflow. It totally depends upon your nature of test cases where low and high both become equal to int max. Okay, but yeah, you can use that. That's a good practice, low plus high minus low by 2. But this concept, which was, I would say, gold of today's lecture, could you relate to it? How many of you completely got this part? Yeah. So see, this is a variation of, I mean, this is known by different names. People call it as binary search on answer. Binary search on answer. Binary search, why it is called as binary search on answer? Because that is what we did. We said that, hey, our answer will lie in between 10 to 90. We picked a particular value of our answer and we tested whether it can be our answer or not. If it cannot be our answer, we either go to the right side or we go to the left side. So this is called as binary search on answer. And there is a fixed template for it. Questions on this category are really hard times, but there is a fixed template once you identify that it belongs to it. So first thing is you identify your monotonic function. Because if you remember, our entire game started when we identified that count function was monotonic. And then second thing is you identify your range. Here our range was from min to max. And then nothing else is needed. Then just apply binary search. That's it. So while I'm saying it sounds like that's it, but then, you need some practice. You need some sufficient practice in order to nail this concept. This question can also be solved using a min heap. also by using a max heap. And in that case, whether that approach is better or not, it depends upon so many things. Are you talking about better in terms of space or time? So in terms of space, this is better because when you use a heap, you are using extra space. First thing. And if you talk about time, the time complexity there depends upon the value of k. Okay, because if the value of k is, let's say, equal to n, then that also would become almost equals to n log n, right? Because when you're saying k log k, if k is equal to n, it would become n log n. So that is conditional. Okay.